All right, hello, my fellow electron microscopy aficionados. Nailed the intro that time. So, um, haven't started on the FFT Part 2 yet, but I did have an opportunity here to put together maybe not just one, but a couple quick hitter videos um, with our Talos system. So the Themis is still being worked on, although, maybe we're kind of 2 weeks out now at this point, but we don't know. So anyways, the thing I want to cover in this video is I want to cover how to do a beam shower with the Talos. Okay, so I do have a video that I posted, I think it was way back in 2018 with the TEM, talking about managing specimen contamination and how to do a beam shower, but I want to kind of go over this a little bit more in detail with the Talos, because it's actually easier to do this with the Talos because we actually can directly measure the beam current, whereas we couldn't do that with the TEM per se. Okay, so anyways, I already loaded up a sample here, so I have a, let me open up the column valves here. So what I've got, so you can see this. Okay, so what I've got basically is a lacy carbon support film with an ultra thin carbon support film over top of that. So these open areas, this is where we have the ultra thin film, which is about 2 nanometers thick. And so you can see right in here and over here, there's a couple of particulates, and this is actually what we're interested in imaging. Okay. So, as I've mentioned many times, plasma cleaning is really your best line of defense to deal with contamination, or I should say prevent it when you are performing your STEM analysis. But it's not always necessarily the best option. So with these support film grids in particular, you have to be careful because they're carbonaceous and the plasma will attack them. So especially with these, like the ultra thin part here, these are, it's about 2 nanometers thick. Okay, so it's not going to take much time to burn completely through that. Okay, and once you do that, you basically lose all the benefit of having the film, right? I mean, because the whole idea is you want your particles to sit over the ultra thin part of the film and be supported by that, and then you can image through it and you're getting minimal distortion from that ultra thin film. Okay, so and I don't know the exact amount of time it takes to go through 2 nanometers of carbon, but it's not much. We're talking about probably a few seconds of cleaning at most. So really with a grid like this, plasma cleaning is not really indicated, okay, if we're being honest here. Let me just mag up a couple clicks here so we can see this. I'm at eccentric height, which is why this is a little hard to see the support film here, okay. So anyways, another option you have is to UV ozone clean, which is really good because that will not attack the film at all. And it can be very effective, but we don't have a cleaner here specifically designed to clean STEM holders for that. We do have a UV ozone cleaner, but it is designed specifically for lithography support. So, I have experimented with using it to try and clean grids, but and it does work to do that, but it's it's complicated to use, right? Because it's not like with the Fashoni plasma cleaner where you put the grid in it in the holder goes into the cleaner, you clean it, you put it right in the microscope. It's not designed like that where we can just conveniently load the holder in. It's designed basically for like cleaning wafers, right? So, and it's also not on the same floor as we have the microscope. Okay, so we would have to go upstairs to use the UV ozone cleaner, then rush down here with the sample, put it into the holder, then put it into the microscope, okay? Which is not ideal either, right? You want that sample to go into the airlock as quickly as you can after it's been cleaned, okay? So anyways, let's say then, you don't have that as an option either, right? So you can't plasma clean, you can't UV ozone clean. What are you left with? Well, your last option is to do what's called a beam shower. Okay, beam shower is different from UV ozone and plasma though, in that it's not actually a true cleaning method. Okay, so let me mag out again here. That's the lowest I can go in SA mode. Okay, so everywhere that we're seeing right now, so this this grid was prepared by drop casting a solution of these particles in isopropyl alcohol, okay, which is an organic solvent, right? So it's probably, I mean, most assuredly will be leaving behind some organic crud with it, okay? Even after it evaporates, which I did give it time to do. I didn't do this in a vacuum furnace, but I did apply a little bit of heat to help facilitate that. But there's still going to be some crud left over, okay? And that crud, at least initially, is distributed over this whole area, okay? Really the whole area of the grid, right? We're just looking at like part of a square right now, okay? And so right now, that contamination is dispersed over a wide area, and it's very, very thin, okay? So what we can do is we can use a high beam current over a wide area, and we can basically lock that contamination in place, and that will prevent it from accumulating when we go to do like high magnification imaging of this particle, okay, where we're taking the beam and we are converging it so it's maybe just a little bit bigger than this particle might be, right? So if we do that, then we don't run into the issue where we're generating a nice, thick, solid chunk of polymer on top of our area that we're imaging, okay, which is what we want to avoid. Because if we do that, then we increase the total thickness. We don't see the detail that we want to see from the particle, and life in general is just not very good at that point. Okay, so so let's talk about doing a beam shower. Okay, so the idea behind beam shower is high current spread out over a wide area. Okay, so let's address the first part of that, which is high current. Okay, how do I get high current? So the first thing is the gun. Okay, so we have an SFEG on this system, and by and large now the service technicians are maintaining the SFEGs at this high extractor. I know there was at some point, they recommended using like lower values depending on your application, whether you're doing TEM versus STEM. But I know now they pretty much always recommend just run it at 4500. So this is basically fixed. But what we can play around with is this, the gun lens. Okay. So the gun lens functions very similar to like the C1 lens. Okay. So as the gun lens goes up, I'm getting more demagnification of my source, right, my FEG tip, and as a result of that, I am reducing my beam current that is going through the rest of the column, okay? So the trade-off, of course, right, is I'm getting more demagnification so I can form smaller probes, but I'm losing current, okay? So if we want to get the most current out of the gun possible, we need to take this gun lens and drop it all the way down to 1, okay? So once you drop it down to 1, you then have to realign the gun, okay? Because the gun alignment is very sensitive to this gun lens setting, okay? It's sensitive to the gun lens, it's sensitive to the extractor, it's sensitive to the voltage. But since, as I mentioned, we don't really play around with the extractor anymore, really the only thing, and we're at 200 kilovolts right now, really the only thing that it's kind of sensitive to, at least at this moment, is the gun lens, okay? So we can drop it from 4 to 1, and then if we do that, we need to realign the gun. Okay, so I've already done that, and I saved that as a FEG register. Okay, so you see here I have 3 FEG registers here for 200. I have one for microprobe or TEM mode, one for nanoprobe or STEM mode, and then I have one that says beam shower. So microprobe, this is gun lens 4, this is gun lens 7 for nanoprobe, and this is gun lens 1 for beam shower. Okay, so now that's part 1 is the gun. Okay, the other thing too is my spot size I need to drag down to 1. Okay, my beam current gets bigger as I go lower in spot size value. Okay, so I'm going to drag this to 1. Okay, and we can already see here that my current went up by about a factor of 4, okay, by doing this, by going from spot 4 to spot 1, okay? And now the other adjustment, and of course I haven't changed the gun yet, we are still on this setting right now. I'm gonna do that in a second here, but the other adjustment is you need to make your C2 aperture the biggest value that is possible, okay? So if I go from 70 to 150, I've basically doubled my diameter. So I'm going to end up with basically a more than 4x increase in the current, okay? Because this ultimately controls how much current reaches the sample as well, okay? So make your C2 aperture big, go to spot size 1, and then the last part of this, I'm going to switch to the FEG register for the beam shower, which again is at gun lens 1. Okay, so now we are getting a lot of current. Okay, right now I don't even have the whole beam on the sample here. Okay, but we're getting close to 100 nanoamps. Okay, so what I want to do, I'm going to stay. I'm not going to go into LM mode. I'm going to just go. I'll go into M, and I'll go down 2 more clicks here. 1, 2. Okay, let me move over here. Okay, so the whole beam is on the screen here, and you can see we're getting almost 130 nanoamps of current. Okay, so a lot of current right now. Okay, so when we were doing the actual imaging in TEM mode, we were using about 1/100th of this current. Okay, so we have a high current, and you can see now the scale bar here in the FluCam, this is not, perfectly accurate, but it's roughly accurate. Okay, so we're spreading this out over, that's roughly about 20 micrometer diameter. Okay, but yeah, you want to use something that's definitely like tens of micrometers as far as your beam size when you do this. Okay, you don't want to be like close to crossover when you do this, or else you're going to end up building the contamination up around this. Okay, so you have to keep the beam spread out. Okay, so let me move this over just a little. Okay, I know that this is the spot, but we're gonna keep it like this. Okay, so this is a beam shower, right? You use a beam that's, maybe tens of micrometers in diameter. You're illuminating your area that you want to fix the contamination on. You're getting the most current you possibly can to do that, right? Which in this case is close to 130 nanoamps. And then we're just going to run this for a few minutes, okay? So, that's another question, right? How long do I need to actually run this in order to see the benefit? So, there's no hard, fast answer for this. I mean, I normally, it could be as short as 5 minutes. I've heard sometimes some people will do like half an hour or more. It kind of depends on how, contaminated things are, right? And how compromised things are. So the cleaner they are, the less of a, issue this is going to be, okay? But let's go ahead then. I probably should have set a little timer here. So let's been talking for about a minute. So let's go ahead and we will run this for an additional 4 minutes here. And then we're gonna go back to our normal beam settings and we will see if we have done a good job of fixing that contamination in place, okay? So again, those of you at home, right, you can just, you can go ahead and, because this part's obviously a little boring, so you can skip ahead to about 3.5 minutes from now, where we start actually looking at the particle, okay? Or actually, I say right about now, go 3 minutes forward, okay? And then you won't have to, you know, wait for the beam shower. So, let's see. Other stuff to we can kind of chat about here while we're waiting for this. So, closing in on the 4,000 subscribers. So, thank you again for that. Part of that, of course, is that I don't get content out as much as you know, as I'd like to. I do have a lot of ideas for videos, and I just, you know, it's hard just to find the time to do it. So um, I do have kind of an exciting announcement about an invited webinar I was invited to give, and once it's become kind of official, I will, you know, also make an official announcement. So um, everybody who follows me here on YouTube can come and see that. But I don't want to divulge too much information yet because this is not yet official, although, you know, for all intents and purposes it is, but it just hasn't been, you know, officially announced by the association that has contacted me. So I'm waiting until that's all done, and then I will divulge away. So the other video I wanted to do, which I might be able to do here, it talks about some weird features that sometimes come up in the diffraction patterns, which I recently got some answers about because I read the manual for the microscope, strangely enough. Okay, so anyways, you know, kind of neither here nor there, but you know, it's one of the kind of quick hitter videos I had an idea for. So this was a couple of weeks ago. I had a couple people, they follow me on YouTube. I think they contacted me on LinkedIn. They were here at a conference. They were from the UK, and they actually traveled over here, and I gave them a tour of my facility, which was a neat experience. So it's always great to, you know, meet people like that. Um, it's kind of amazing what things like the internet and social media can do to help shrink our world. So, all right, we only got about 15 seconds left here on the beam shower, and then we will see what we've got here and see if we're avoiding contamination. And done. Okay, so we're going to go back to the microprobe FEG register. We're going to go back to spot size 4, and we're going to go back to the 70 micron C2 aperture. Yes, and this should get us around 1.4 nanoamps. Okay. All right. So now again, we're doing this raw, unedited, unfiltered, and uncut. Okay. So I don't know that this is going to work. I'm confident that it will, but you know, again, no guarantees, right? I'm gonna check my alignment here really quick. Okay, my C2 aperture is off. just like I would expect it to be. Okay, that's decent. All right, so we got two kind of spots here, so I'm gonna ignore this one and we're gonna concentrate on this guy on the left here. So you can see, right, it looks like it's suspended over nothing, which is great because it means I still have the film intact right here, okay? All right, let's check our pivot points. Okay, looks good. All right, we can mag up a little more here. Check our rotation center. That looks great. All right, so let's go to diffraction. And I wonder if I'm on the wrong side of crossover here. Kind of looks like I am. Let me pull this out of the way here. Okay, you always want to be clockwise from crossover. There's a little bit of condenser astigmatism. Let me fix that. Okay, there we go. I could kind of tell from the diffraction pattern that I wasn't quite on the right side of crossover. Or actually, no, I was. Oh, I had my camera link high. That's why. Duh. Okay. No, I was doing that because I was trying to look at something else. Yeah, so this actually looks pretty normal here. Okay, so I wasn't on the wrong side of this. So, all right, let me turn off diffraction stigmator. Add that to the blooper reel. All right, put in my 70 micron objective, which is optimal for doing high res. So we're seeing some crystalline diffraction, which is good. This is what I was hoping to see here. So this was one of the particles that we were hoping to see. Okay. Check our beam here. All right. Acquisition. We'll start around, yeah, around 200 milliseconds. But yeah, it looks good. Okay. So now again, if you've seen my video on focusing, right, where I haven't adjusted the focus knob yet, I'm going to see if I can get this a little closer here by adjusting Z. This is a little tricky though because this is not flat, okay? There's a bunch of topography here, but I can tell that we're under focused. So that means I need to go up. Yep, so that's much better right there. Okay, now there's probably some astigmatism. It's gonna be a little tricky to correct it now, although I can try. Okay, I push, yep, stigmator, that gives me objective. What am I on, step 3? Yeah, so this is gonna be a little easier at the next mag, but I'll leave it alone for right now. All right, so let's take a snap, or an image. Okay, all right, so there's definitely some astigmatism here. So one other thing we can do, we can temporarily bump up the pixel resolution, and that allows us to see, right, because you saw my video on FFT, wider angular range. Okay, looks good. Let me move up here to the top end of the particle. Okay, looks decent. All right, I'm gonna mag up to 500K. Just my beam again. All right, so we can see lattice here. Looks pretty good. Oops. Okay, that's pretty good right there. Okay, looks good. Now this is, obviously this particle is polycrystalline, so we're seeing kind of a hodgepodge um, of different lattice fringes, right, as we should. That was coming out in the FFT as well as the diffraction pattern. We also have a little drift. Yeah, so I can see that in the FFT. So that's another video I want to do here. I might do that after this one's done, talking about how to do DCFI for TEM mode. I know I've covered this in STEM mode, but you can also do it in TEM mode, and it also works really well. Okay. Yeah, see, judging by the FFT, we might have a little bit of motion this way, but it's not terrible. We're not losing like a tremendous amount of detail. But this would work really good for doing DCFI, which I will actually. Executive decision, I'm going to piggyback off of this, and I'm going to do DCFI, video on DCFI for TEM mode when this is done. But as you can see, right, we're getting nice images here, okay? We're not really getting any contamination buildup. I mean, everything looks good, okay? So it looks like the beam shower did its trick. Now, the way we're going to tell, though, is actually when we're done here, and I'll show you what I mean here in just a second. Okay, good. All right, so now what I'm going to do is I'm going to mag down here several clicks. Okay, and we're going to look at the specimen over a wider area here, or the particle, I should say. Okay, and so you can kind of see maybe like there's a little bit right here, but really not a whole lot. I mean, if we were getting contamination buildup, we would see dark blobs everywhere that we were illuminating, and we really don't. Okay, so the beam shower, by all accounts, I would say was quite effective. Okay, and again, that's just doing it for 5 minutes, right? I mean, we could have done it for 10, right? But obviously, I didn't want to stretch the video out that long, make everyone wait for it. So, okay, all right. So that is the video on doing a beam shower on the Talos. So what I'm going to do now is I am going to um, switch, and I'm going to do another quick one here on doing DCFI for doing TEM mode, okay? So hopefully you'll stick around, and that one will be next. All right, take care, everyone.